In order for us to be better at solving systems, we've got to be able to quickly convert from equations to matrices and matrices back to equations. We already know how to convert a system of linear equations into a matrix representation. And here we have a system, a 3 by 3 system. It has 3 equations and 3 variables. And this is a 3 by 3 system. So once again, these represent, this first value is the number of rows. So I have 1, 2, 3 rows. This is so 3 equations. And then I also have 1, 2, 3 columns. Notice that we have our x, and I'm going to kind of circle around here because this 2y does not contain an x in it. And then my second column, I have all of my y variables, which again, second equation, I don't have a y variable explicitly stated. And then in my third column, I have all of the z's, which there they are. And so there's 3 equations, and there are 3 columns, which represents the number of variables. So I have 3 variables here. So to convert this, the important part is that we should be able to represent the coefficients of x in the first column. So here's my 3 equations that will be listed in here along the rows 1, 2, and 3. And I'm going to list along the columns the variables, which are in this case called x, y, and z. The names of the variables are really not important. We could call them x1, x2, x3. We could call them PRQ. We could call them whatever we want. This system just happens to have the labels x, y, and z for the variables. So in the first equation, we have coefficients of 1, 2, and 3. And it's important that we list the variables first. It doesn't have to be in alphabetic order. It just has to maintain that a column contains only the coefficients for that variable for which it's intended. And then over here, we kind of like to draw this dotted line. This dotted line is not necessary, but it's helpful visually to indicate that that's where the equal sign is. And on the right-hand side, we list all of the constants. So that's the constant 4. And in the second equation, I can see I have a 1x. I do not have any y's in it, so I could always write a plus 0y in here if I wanted to. And I have negative 2 copies of z, and my constant is 10. If these were not all arranged such that we had the constants on the right and the variables on the left, we would have to do some rearranging of the equations, moving things from one side to the other in order to get variable, variable, variable constants. In the third equation, you've got to be careful because, again, here I'm missing an x variable. Therefore, I have 0 copies of x. I have 2 copies of y, and I have 5 copies of z. And the constant that equals is the constant 19. Now, a lot of times, if you're using a calculator or using some sort of technology, you're not going to see this dotted line. So we'll simply see the system 1, 2, 3, 4, 1, 0, negative 2, 10, 0, 2, 5, and 19. Now, if I asked you to read off what these equations are that this matrix represents, assuming that this fourth column here is always going to be the constants, and I tell you that up front, then if I didn't tell you the names of the variables, you could name them whatever you want. You could name them P, Q, and R if you chose. But since we know they're called X, Y, and Z, and this corresponds to the coefficients of X, the coefficients of Y, the coefficients of Z, equals constants, and the rows represent, again, the equations themselves, I could easily read this off and say that this first row represents the equation 1x plus 2y plus 3z equals 4. Second row, 1x plus 0y, or I could omit the y variable altogether as it is in the second equation, minus 2z equals 10. And for the third row, 0x plus 2y plus 5z equals 19. So let's go ahead and do that. Here we have a system, and I'm telling you that this is a representation of a system of equations. I haven't named the variables, so at this point you could choose whatever you want to call the variables. But this is row 1, row 2, row 3 corresponding to our 3 equations. And because we're using x, y, and z, let's just go ahead and say this is x, y, z, and your constants. So the first row then reads 3 times x plus 1 times y plus 0 times z equals positive 4. And these are always added together. The only time it ends up with a minus sign is if one of the coefficients is negative. So in the second row, we have 0x plus 4y minus 1z equals 7. And in the third row, we have 2x plus 0y plus 6z equals 8. And this is our system of linear equations. So you can see we can easily convert between the two, and we're often going to want to operate on the matrix itself, so we'll often be converting a system into a matrix, and once we do some things to that matrix, we're going to convert it back. So we're often going to start with a system of linear equations, we're going to convert it to a matrix, we're going to do stuff, and that stuff will become more apparent soon. And then once we do stuff, we're going to write this as a system of linear equations, which will actually end up containing the solution. Let's go ahead and do one more. In this system, there's lots of ones and zeros, but again, I'm looking at this in exactly the same light. I have equation 1, equation 2, equation 3. The rows will always contain our equations. The columns are going to contain our variables. So to change things up, I'm going to refer to these coefficients, 1, 0, 0 going down. I'm going to refer to that as the coefficients of some variable called x1. I'm going to refer to these coefficients as coefficients of some variable called x2, x3, and then as usual, if this is representing a system, these would be our constants. And in between the constants and the 3 columns to the left of those constants, that is going to be an equal sign. So in our first equation, we have 1x plus 0y plus 0z equals 2. The second equation, we have 0x plus 1y plus 0z equals 9. And in the third equation, we have 0x plus 0y plus 1z equals 2. You might be looking at this and saying, well, doesn't this really tell me what x1, x2, and x3 are? And of course, I've made the mistake of using y and z in place of x2 and x3, so let's go ahead and update that. So this is x1, x1, x1. We have our x2 column, and then we have our x3 column. Again, the name of the variables is arbitrary, you just have to decide on that up front, unless it's explicitly stated that the columns represent certain variable names. So in the first equation, of course, we don't need the 0x2 and the 0x3. What this really reads is that x1 is equal to 2. In the second line, we see that really this is just saying x2 is equal to 9. And this third row is saying x3 is equal to 2. So in fact, what we have here is a solution set. And the solution set to whatever system was originally being represented, let's just suppose that back in our previous step here, there's some do stuff component, and this is the result of that do stuff. And therefore, our solution set could be listed in a couple of different ways. We could say that the ordered triple, we call this an ordered triple. Why do we call it that? Well, because the values are ordered in a certain way, x1, then x2, then x3. It's a triple because there's 1, 2, 3 values. And the ordered triple is going to equal 2, 9, 2. Another way we could state it is in vector form. We could say x1, x2, x3 vector is equal to 2, 9, 2. There's already an apparent connection between what we do when we solve a system and some sort of vector form. This system here, the form of this, the form that this has, this 1, 0, 0, 0, 1, 0, and 0, 0, 1, and only ones along the diagonal, and then we see zeros everywhere else. This is called reduced row echelon form. And that's something we'll learn to obtain, because if we can get a system into this form, then we have effectively solved it. This is called reduced row echelon form. A lot more on this to come.